Okay, so continuing on. This is how you date artifacts, fossils, rocks. Now, some things you can date with carbon-14. Other things need to be a little bit longer lived than that. We'll talk about that in just a second. But anyway, it may be a little bit weird to think, how do they know what percentage is actually still left? It's like they weren't there when the fossil started. But what they can do, and this is how they get clever, is they can see how much of the product of decay is in the bone compared to what should be there. Like, for instance, carbon-14 decays to nitrogen-14. So they look at the carbon-14 to nitrogen-14 ratio, and they can begin to understand how much carbon-14 used to be there. So here's the question. If only 1/8 of the original carbon-14 in a rock sample still exists, what's the age of the sample? So for that, you need table N, and also you need to think about how many half-lives have passed to have only 1/8 of the original amount remaining. So press pause, please, and take 3 minutes with your groups and do that. Okay, now that you're back, you could have done this with a half-life table. Any way you like. You could find out that it's a half times a half times a half gives you an eighth, right? A half. And since that's the case, that means you went through 3 half-lives to get to an eighth. That's another way to do it. So it's 3 half-lives. So 3 half-lives. And then you go to table N. And I know it's 5715, but let's just show you where it is. Carbon-14. There you go. Carbon-14, 5715 years. So if you have 3 half-lives and each one is 5715 years, 5715 is, let's see here, 45 at the end, and then 3 times 57 is 171. 20,145 years. But that's what you'd be talking about. Only 1/8 of the carbon-14 exists. Now, with a half-life of 5715, that's a really cruddy way to date certain organisms. So here's the question. Is carbon-14 better suited for finding the fossil age of woolly mammoth or of brontosaurus? Quickly talk to your groups and decide. Which one is it? Say it. Woolly mammoth, because you can't go millions of years out on this stuff. You need such a minute amount of carbon-14 left to get out to millions of years. So in fact, radioactive dating is used, so we should be a little more specific. Carbon-14 used for organic matter and recent fossils. But we need something longer lived for things like dinosaurs. So in fact, the one that's used for dinosaurs most is uranium-238. Relatively stable. It's radioactive, but over a very long period of time. Used for older fossils, like dinosaurs. If you look at uranium-238 on table N, you will see that its half-life is 4.47 billion years. So you don't have any problems of it running out. You'll have half of it and be a billion years old. So you can easily do millions of years, just won't have half of it gone, and that's okay. But that will be a longer-lived isotope that you can use for older fossils, and that's how a lot of the fossils that we see are dated, and that's how we know certain dinosaurs were around at certain periods of time. And you are 60% done with the unit. Just like that. All right. Yeah, I think I'd like to do a little bit of this here on page 7. Fission and fusion. Look, one of the uses of nuclear chemistry is in the production of energy. It's a big deal. We're not going to discuss all the parts of a nuclear reactor. That used to be part of the Regents curriculum, but no longer. We're going to briefly mention the reactions that take place in nuclear reactors, and also the reactions of our biggest natural nuclear reactor, which is the sun. And the sun does give us our energy from nuclear processes. So fission. Here's the definition of fission. It is the splitting of a large, unstable atom into 2 or more smaller atoms. In this process, a very small amount of mass is lost. If you did the arithmetic on the nuclear reaction, you won't see it. I'm talking like 0.1, 0.05, something like that. Very small amount of mass is lost in this process. This mass is converted into a lot of it, according to an equation. According to E equals the equation that describes. So the very small amount of mass that you lose gets multiplied by the speed of light twice to give you joules, and you end up with a lot of joules at a very small amount of mass lost. If I have an opportunity in class, I'll show you the calculation. It's really impressive. And that's fission. Fission, the split, kind of like binary fission. When, you remember bacteria splitting, binary fission, an asexual reproduction method. So fission means split, and that's what you got. Fusion, on the other hand, is the joining of two small nuclei into a larger atom. In this process, also, a small amount of mass. You won't see it in the arithmetic. It could be 2 plus 2 on one side and 4 on the other, and that's what you will see. But really, the 2 plus 2 is like 3.9, and that 0.1 loss gets converted to energy the same way. However, the amount of mass lost in fusion is actually a little bit greater, and so this mass is converted into super huge amounts of energy, even more than fission. Now, and this is also according to E equals mc squared. Just one catch further down here. One catch is that fusion, if you look at the bottom of 7, has to happen at more than 40 million degrees Celsius. That's not easy to do down here. Right now, all of our nuclear reactors are fission reactors. Fusion reactors, something people want, would be really useful, but you have this issue. We just don't have 40 million degrees Celsius very easily. There are ways to do it in small pieces, in small areas, small volumes, and people are working on it, but that's the biggest problem for fusion. In each of these processes, mass is lost, and when an atom splits or 2 atoms are fused, this mass is converted into energy. You can write that again there. This is an important property. So let's take a look at what fission looks like. And if you needed to press pause here, you certainly can to write this stuff. I know I was typing quickly. Uranium-235 captures neutrons. If you put a neutron beam at uranium-235, it makes a nuclide, which I want you guys to write in your groups. It's very unstable. It then immediately spits out 3 neutrons, a krypton-91, a barium-142, and a lot of energy. This is fusion. I want you to write down that very unstable nucleus that is one that immediately breaks down. You'll notice that you have 2 atoms that are not split in half, but definitely split. It's not like getting just like a beta particle. That's not a fission. It has to be 2 sizable elements. This reaction produces a lot of energy. The equation is E equals mc squared. We're not going to be asking you to do any calculations with that. That's it. The other direction is fusion. You can press pause to get this nuclide in there. You might have already written it in because this is a pretty easy nuclear reaction, especially on this side. Fusion, 2 small nuclei are fused together. Think about how hard that's going to be to do. You have all these protons, and you want to not only you want them close to each other, which are not going to like to do anyway because of plus and plus. You want to bring this, like if I were to draw it. That's not going to let me. That's the end of the page. All right, fine. Put a plus over here, another plus over here. That's one thing. But then you want to put them right on top of each other. Good luck. Okay. That takes so much energy to fuse them together and make them a new element. The sun can do it. And here's how the sun does it. It takes 4 protons, makes a helium, 2 positrons, and a ton of energy. On our planet, this is how we would do it. I'm not going to go nuts about this. I am going to leave you an assignment now, though, using these types of things in your nuclear review homework. Okay? Thanks so much, guys. Have a great weekend.